Welcome to today's briefing. As a milling consultant, I'm here to conduct a high-level audit of the foundational constraints governing your milling economics. Specifically, we're going to analyze the precise engineering tolerances required across your wheat break and reduction systems. Our goal? Maximizing pure endosperm yield while maintaining strict structural integrity. The operational transition between these two systems is exactly what dictates the commercial viability of a facility. So we'll be breaking down the exact tempering protocols, paying very close attention to the 17.5% moisture threshold for hard wheats, and mapping out how these specific structural inputs control the mathematical certainty of your final 70% extraction rate.
Right out of the gate, the primary operational constraint we face in any extraction process is kernel morphology. We have to talk about the aleurone layer. If you look closely, this structure is essentially a single layer of thick-walled cubical cells that tightly covers the starchy endosperm. And these cellular walls are packed with aleurone granules, highly concentrated with ash, phytate phosphorus, and raw mineral matter. Our core engineering objective is the complete intact separation of this layer from the endosperm. It's highly sensitive. Any micro-deviation in your physical conditioning subjects these high mineral granules to intense mechanical shear on the milling floor. If that happens, the aleurone layer is pulverized right into your pure endosperm stream, immediately compromising your extraction purity.
Let's be clear, Bran shatter is just another term for immediate profit loss. High-efficiency milling is absolutely not a process of blunt force crushing. It is a highly calibrated structural disassembly. You have to surgically separate the tough outer bran and aleurone granules from the starchy endosperm. And that separation is dictated entirely by aggressive, mathematically precise moisture control. The physics here require the outer bran to achieve a tough, leathery state to resist fracturing, while the internal endosperm has to hit a highly specific friable state. That friability is non-negotiable, because the internal starch matrix must yield under specific pressure vectors rather than just shattering. Without that exact physical differentiation, your extraction yields will drop exponentially as your final ash content spikes.
Now, the operational mechanics change drastically based on the grain's inherent physical properties. Hard wheat demands extreme conditioning precision, simply because its internal starch-protein cohesion is fundamentally different from soft wheat. In hard wheats, the protein matrix adheres with immense structural tightness directly to the starch granules. This high-tension bond is what defines the kernel's hardness, and it dictates the heavy vector forces required to break it. Soft wheats, on the other hand, have loose cohesion, allowing them to fracture easily along cell walls with minimal force. Because of this, hard wheats require complex chemical manipulation through targeted moisture. We use moisture to precisely weaken that tight protein bond, allowing the mechanical systems to fracture the kernel properly without blowing the entire structure into dust.
The operational data is absolute regarding this initial input metric. Hard-kerneled wheats require exactly 17.5% moisture tempering. Facility operators have to hold this precise target for up to 24 hours to achieve the necessary chemical manipulation. Time and moisture volume work in strict tandem here. Over the first 12 hours, capillary action slowly pulls the surface moisture through the outer bran layers. By the 24-hour mark, that hydration has migrated perfectly to the center of the endosperm. This 17.5% baseline is the maximum mathematical peak for hard wheats before structural integrity fails entirely. It optimally toughens the bran to withstand the shear force of the corrugated rollers, while adequately mellowing that internal starch matrix.
So what happens if we overshoot that moisture threshold? Processing error alert. Deviation above 17.5% initiates systemic mechanical failure across your entire production floor. Overtempering forces the endosperm past optimal friability into a highly hydrated, sticky, mealy state. And once this sticky stock hits the downstream reduction system, it fundamentally alters your fluid dynamics. The wet starch adheres to the fine micrometer meshes of the plan sifter, a condition we call blinding the sieves. When these microscopic apertures are blocked, material stops grading entirely. Sieve blinding effectively closes off the plan sifter flow, creates an immediate operational bottleneck, and forces a dead halt of the reduction line. Moisture is your primary tool, but over-application is a systemic contaminant.
Once we clear the conditioning holds, the stock enters the break system. This is where we deploy pairs of corrugated chilled iron rollers to systematically unroll the kernel. Remember, we are explicitly avoiding a crushing action here. The objective is highly controlled shearing. The architecture typically uses 4 to 5 distinct sets of these fluted rolls in sequence. The flute profiles dictate the aggression of the shear. The first break aims to cleanly slice open the kernel, while the subsequent passes scrape the endosperm away from the bran. Each mechanical pass is immediately followed by a grading operation to extract the released material, before we route the remaining particles to tighter break rolls.
The entire physics of this break system relies on one strict parameter, the 2.5 to 1 speed differential.
These corrugated brake rollers operate in pairs, revolving in opposite directions to create specific vector forces. The fast roll travels exactly 2.5 times the speed of the slow roll. This rotational asymmetry generates the critical scraping effect. As the weed passes through the nip, the slow roll holds the tough, moisture-conditioned bran layer steady, while the fast roll applies a forward vector force to drag the friable endosperm away. This precise differential calculates exactly enough force to detach the starch without slicing the tough bran layer into microscopic, unsiftable shards.
If that 2.5 to 1 ratio narrows, we have a standard maintenance failure known as differential drift. It fundamentally alters the mechanical action of your primary machines. When that differential drops, the precise scraping vector degrades into a blunt crushing action. Your facility will inadvertently pulverize the outer bran layer into a microscopic powder, rather than maintaining it in large, manageable flakes. Once this unsiftable bran powder mixes into your fine flour stock, it is mechanically impossible to separate using standard plan sifter technology. The immediate statistical consequence? A sudden, uncontrollable surge in final ash content, an immediate downgrade of your primary product, and a significant hit to your operational margin.
The released material from these brake rolls immediately enters the plan sifter architecture. Here, the equipment grades the stock into 4 distinct fractions based on strict micrometer thresholds. Materials larger than 750 micrometers are coarse offals and unreduced endosperm, which get routed back to the next brake pass. Particles between 300 and 750 micrometers are Semolina. The 125 to 300 range isolates the Middlings. Anything falling below 125 micrometers is fine flour. This strict precision grading dictates your entire loading strategy for the upcoming reduction stage. Semolina, due to its larger mass, requires a significantly different roll gap and reduction setting than a smaller Middlings to ensure uniform particle size distribution.
Now we hit a critical pivot, the operational transition from the brake system to the reduction system. This marks a fundamental shift in our mechanical strategy. We swap corrugated rollers for entirely smooth rollers. The engineering objective shifts aggressively from scraping the bran to crushing the pure endosperm particles, the semolina and middlings, into fine flour. To execute this properly, the speed differential must be intentionally lowered to a 4 to 5 ratio in Europe or a 2 to 3 ratio in North American facilities. Lowering this differential is critical for thermal dynamic management. If you maintained the high 2.5 to 1 brake differential with smooth rollers, the friction would generate extreme heat, actively degrading the starch granules and destroying your flour's functional baking characteristics.
We have to be incredibly precise here. As standard milling techs warn regarding fluid dynamics on the line, the flour easily sticks together and sifts with difficulty, tending to close the apertures of sieves. Improper reduction settings, especially with softer wheats where cellular cohesion is already mathematically low, cause fragmented starch particles to compress and clump. This adhesion phenomenon blinds the sieves. When those micrometer apertures plug up, your system throughput mathematically drops to 0. The stock backs up the entire sequential flow, severely bottlenecking efficiency. The resultant downtime cost from clearing a blinded plant sifter run exceptionally high, destroying your daily yield metrics.
Ultimately, the entire engineering objective of this sequential breaking, reducing, and sifting architecture is to consistently hit the commercial baseline, the 70% extraction rate. This is our hard economic ceiling. Out of the raw, whole grain volume, exactly 70% should be captured as pure white flour. The remaining 30%, categorized as offals, bran, and shorts, represents a strictly protective boundary. Sure, pushing past the point of diminishing returns to a 72 or 74% extraction is mechanically possible by tightening roll gaps, but coldly analyzing the data shows that exceeding 70% drastically increases the statistical probability of aleurone contamination, fundamentally degrading the purity of your entire batch for a negligible volume increase.
At the end of the day, gross yield volume is a secondary metric to verified product purity. The definitive indicator of a successful operational extraction is a strict 0.45% ash content limit. This specific metric is your internal quality assurance verification of that 70% yield target. Ash content directly measures the mineral residue left after sample incineration. Because the pure internal starchy endosperm mathematically contains roughly 0.3% ash, while the bran and aleurone layers hover around 5 to 6%, any final flour analysis reading above 0.45% is hard, mathematical proof that your mechanical bran separation has failed and structural contaminants have bypassed the sifter.
If your ash content creeps toward 0.60%, you are looking at a systemic mechanical separation failure and instant margin degradation. The facility is fundamentally missing its target metrics.
The data dictates the baseline, from that initial 17.5% moisture application down to the final smooth roller gap. So I'll leave you with this final audit question. Are your facility's differential tolerances and tempering protocols mathematically optimized to consistently hit the 0.45% purity standard, or is your line currently operating at a persistent structural deficit that requires immediate mechanical auditing? The separation between a highly profitable facility and one that struggles with yield degradation lies entirely within these exact millimeter adjustments.